Hi kiddos, we're talking 12.3 today. This is the experimental probability versus theoretical probability section of chapter 12. It's the fun stuff. Alright, so I have a couple warm-up problems that are related to 12.2. We'll share them with you so you know how to do them, and then again, I may or may not be at school because of my son, the new one. Yeah, the new one. Yeah, he might be born, so I made a video for you anyway. So we have find the probability that the first is a dime and that the second is a quarter. So there's a total of 30 coins here, and then the first one being a dime, so there's 10 out of 30 that are dimes. And then up here it says without replacement, so now I'm at 29 coins for my next one, and it says then a second one's a quarter, and there's 5 quarters, so multiply those two numbers together in my calculator, and when they simplify I get this for my answer of 5/87. So we just plug that stuff in the calculator. Alright, find the probability that they are both nickels. So the first one is 15 out of 30, which is 1/2. But we'll leave it as 15 out of 30, and then since a nickel's been removed, now there's only 14 nickels left out of the 29. So you multiply those two things together, and a simplified answer is 7/29. So that's the information for what we did in 12.2, and now we're moving on to 12.3. So why aren't theoretical and experimental probability the same? So here's our words here. Experimental probability is the probability based off of an experiment. It's what did happen. The theoretical probability is based off of characteristics or facts. It's what should happen. So you could almost already answer our essential question because one's happening from an experiment and one's happening from what should have happened in the experiment if you did the event enough times. So here's our example. Nikki is conducting an experiment to find the probability of getting various results when 3 coins are tossed. The results of her experiment are given below. So our job is to find what is the theoretical probability of tossing all heads on the next turn. So what we need to do is figure out how many tosses we had total, and then all heads was 6 out of the total number of tosses. So I'm going to take my calculator and I'm going to add the total number of things that happened. So we had 6 plus 32 plus 30 plus 12, and that's a total of 80. So the probability of her getting all heads next time is in 6 out of 80 according to the experiment. Now 6 out of 80 simplifies when we divide them both by 2. Simplifies to 3/40. So there's a 3/40 probability that she would get a all heads on the next time. Now question B says according to the, oh, I did that one wrong, folks. That's the experimental probability. We need to go back and do the theory. Now if you look in theoretical worlds here, we have 1, 2, 3, 4 choices, right? So the 4 choices, there's a 1 in 4 choice that we're going to get the probability of being all heads. So this is the experimental, this is theoretical. So what should have happened is we should have had 1/4. So this is not the correct answer. I goofed. This is the correct answer. There's a 1/4 chance in theory that she will get all heads. My bad. But it's good for you guys to see me make mistakes too, because that doesn't happen very often. So we'll move on to part B now for official business. The experimental probability that Nikki is more likely to get all heads or no heads on her tosses. All heads was 6 out of 80. No heads was 12 out of 80. So is it more likely for her to get 6 or 12? Well, that's fairly simple to look at. 12 is a bigger number. So the experimental probability says that there's more likely to get no heads than there are to get all heads. My bad, folks. We're moving forward. All right. Example number 2. 800 adults, I'm going to write that down, that's important, were asked whether they were planning to stay home on winter vacation. Of those surveyed, 560 said that they were. So they're going to stay home. What is the experimental probability that an adult planned to stay home for winter vacation? So 560 out of the 800 said that they were going to stay home. So we would take into our calculators and we would simplify 560 over 800, and that simplifies to 7/10. So 7 out of 10 people would stay home for their winter vacation. Sounds like me. I'd never leave anywhere other than to come to school or basketball. All right, example 3. Over the past 3 years, the probability that the school's math team, I coached that, would win a meet is 3 out of 5. Is this probability experimental or theoretical? Now this is totally experimental because we're talking about what has happened in the past. So it's 3 out of 5 years we have won the meet. So that's based off of an experiment. So that's why it's experimental. Part A, if the team competes in 35 meets, how many can they expect to win? So 3 out of 5 they win. If they go to 35 of them, how many will they win? So this is just a simple any proportion. So we did times 7, you can expect them to win 21 out of 35 meets. So they win 21 times out of 35. It's a pretty good average, folks. That's 60% of the time that's winning. Now, if the team wants to win 12 more meets in the next 3 years, how many meets should the team enter? So they want to win 12 more. Folks, I had to pause for a second. I got a message from my wife talking about pregnancy stuff. So here we are again. If the team wants to win 12 more meets in the year, how many do they need to enter? So if they win 3 out of 5 and they want to win 12, how many should they enter? Well, it's the same kind of a thing. 3 gets multiplied by 4, so they need to enter 20. They should enter 20 meets if they want to win 12. All right, folks. This is the last problem. Make sure you write your summary. You can work on your 12-3 assignment. Best of luck to you. Let me know if you have any questions. Shoot me an email, or we'll see you in school.